In this part, we are focusing on preliminary knowledge required for understanding blockchain technology. As we will see in the next section, blockchain takes a central authority out of the equation. This is achieved through introducing the concept of proof of work, or to be more specific, proof of computational work. And solving a puzzle is one way to demonstrate that computational work has been performed, since this process usually takes time and computational effort. However, if a solution is given, it's quite easy to verify that this solution is indeed correct, and in such a way it's a proof that computational work has been done. So take a Sudoku game. So that's the most popular puzzle game of all time. The goal of Sudoku is to fill a 9x9 grid with numbers, so that each row, each column, and 3x3 sections contain all the digits between 1 and 9. So let's say that this is our initial state and initial state of the board. Now we want to solve this, to find such kind of digits. It's gonna take time. But as soon as we found the solution, it's relatively easy, or way more easy in fact, to verify that this solution is correct. We just check that every cell in a row, or in each of these columns, or in each of these 3x3 sections, contains all digits. Right? So relatively easy compared to finding, so this is kind of a combinatorial search here, finding all the digits that satisfy given rules. So this idea of solving a puzzle is the basis of proof of work that we will discuss in next section. Instead of solving a Sudoku puzzle, Bitcoin relies on so-called cryptographic hash functions. Functions that are easy to compute but hard to find an inverse. And finding an inverse of such hash function is the puzzle that Bitcoin solves, or Bitcoin network solves all the time. Hash functions, Sudoku, and many other problems rely on the assumptions that P and NP classes are not equal. So what is those classes? So P is a set of relatively easy problems. So let's say we want to compute a product of 89 and 97. The computational complexity of the school book long multiplication is O of n squared. So in other words, for a number of n bit length, we will need n square computational operations. Generally, n's, n square, and n's raised to other powers is called a polynomial. And that is what the P in P versus NP stands for. NP is a set that includes what seems to be very hard problems. So, for example, finding the prime numbers that multiply together to form a number 8633 is much harder problem than just multiplying 89 and 97, which are actually the factors of this number. The complexity of a simple number factoring algorithm is O of 2 to the n divided by 2. So n here is the number of bits. The number of required operations grows exponentially, which is much faster than a polynomial. As mentioned earlier, a hash function is any function that can be used to map data of arbitrary size to fixed size values. The values returned by a hash function are called hash values, hashes, or digests. Hash functions scramble the bits of the arguments so that the resultant values are uniformly distributed. The domain of hash function is much larger than the range of that function. In fact, the domain could contain infinitely many elements. For example, think of all possible strings. Each of the string is an input to a hash function. Having said that, the output, the values that hash function takes, is finite. So you could have simply two inputs two different inputs that are mapped to the same output. Cryptographic hash function is also a one-way function. However, one main difference is that this is a function that's practically infeasible to invert. Some of the additional properties include infeasibility to generate a message argument that yields a given hash value, infeasibility to find two different messages with the same hash value, and besides, a small change to a message should result in a hash value extensively different from the original message. Some popular algorithms that implement hash functions are MD5 and SHA-2. These tables just demonstrate some of the examples of arguments that are very similar, however result in very different outputs. So here we have hello world and here we have hello world, but the first string starts with a capital and the second string begins with a lowercase letter. And you can see the outputs are significantly different. And that is one of the important properties of cryptographic hash functions, that it's first of all hard to predict the output, so it almost appears random, and for two very similar inputs you'll get absolutely different outputs. Bitcoin uses SHA-2, or more specifically SHA-256, meaning that this function generates a string of 250 bits. So here it's this 250-bit number is written in hexadecimal notation, so every digit here is 4 bits, so it should be 64 characters here. So if you multiply by 4, it's going to be 256 bits. Blockchain does not require participants to trust each other. On the contrary, participants trust that the whole network will stay consistent, which in turn is guaranteed by cryptographic algorithms. Cryptographic algorithms is the crucial part of the blockchain. The language of cryptography consists of such terms as plain text, ciphertext, private and public keys, so encryption and decryption keys, and a digital signature. Plain text is an unencrypted message. Ciphertext is corresponding encrypted version of the text, and encryption scrambles the message in some kind of unintelligent representation that is called ciphertext. This text, the ciphertext, is completely useless unless it is decrypted. In telecommunication, when two parties communicate with each other over a public channel, the message should be first encrypted at the sender side and decrypted at the receiver side. Some potential pitfalls of communicating over public channels are message interception, message insertion, or impersonation of a sender or a receiver. There are two types of cryptographic systems: symmetric, when the same key is used for encryption and decryption, and asymmetric. So messages are encrypted with a secret key. Think of it as a password, and obviously this key should be kept private. In symmetric cryptography, the same key is used for encryption and decryption. The question is, how can the sender, let's say, let the receiver know its private key, its secret key, so the receiver could actually read the messages? Well, that's the fundamental question. And if the key, for example, is sent unencrypted, the intruder could simply intercept the key and consequently read all the following messages. To solve this problem, asymmetric cryptography was proposed. In asymmetric cryptography, each participant creates two mathematically linked keys: a public key, here is denoted by the plus sign, and a private key is denoted by the minus sign. Generally, there are two different applications of asymmetric cryptography. One is for secure communication, and two as a digital signature. So usually, asymmetric cryptography is used in the initial stage of communication to exchange symmetric keys. So when symmetric key has been sent, then the communication channel switch to symmetric cryptography because it's more computationally efficient. So to be specific, in this first scenario, the public key is freely distributed to all participants and is used for encrypted messages. The private key is then employed to decrypt the messages. So anyone could encrypt, but only one entity with the private key could decrypt and read these messages. In the second scenario or second application, private key will serve as a digital signature, and the public key then could be used to verify that some document was indeed signed with the private key, since both of these keys are mathematically linked. The process of signing messages digitally deserves a bit more attention. Consider a hypothetical example. Bob digitally signs a document establishing he is the document owner or creator. Then Alice can prove someone else that Bob and no one else, including Alice, must have signed the document. For instance, this digital signature could be used to prove that Bob signed a document that legally transfers the ownership of a house from Bob to Alice. So let's elaborate on this example a bit more. It's an important example. So assume the document is signed or encrypted with the private key and passed along with the original plaintext document. So we have plaintext document M and the encrypted version of this document. Then public key is used to decrypt the encrypted version of the document. So here it's K minus of M. So that's the encrypted version of the document. This encrypted version then decrypted by the public key, which is known to everyone, including Alice, to obtain a decrypted message. And if this message indeed is equal to the message that is passed together with the signed document, or passed together with the signature, which is the encrypted document, then Bob indeed signed the document. This allows Alice to verify that Bob signed M and no one else. Furthermore, Alice can prove that message M was signed and not its modified version M prime. Otherwise, Bob could have modified the document in his favor later on, which would be the M prime in this example. So Alice can now take M, the document, and Bob's signature, which is the encrypted document M with the private key, and private key only, and only Bob possesses this private key and nobody else. So Alice again could take this document M and the encrypted version, which is the sign, to the court and prove that Bob signed this document. Let's say change of ownership or something like this. So that is the end of part 2, and we're moving on to part 3.